Hello and welcome back to STEM Online Academy. My name is Jason Masterakos. So, what we're going to be looking at today is we're going to look at something interesting about the natural log function. Okay, so here we go. So, most students can differentiate ln of 1 plus x over x. However, far fewer can prove what it means geometrically and determine exactly when the secant slope from the origin will be maximized. So in this video, we will solve a hard calculus problem that involves g of x here, right? G of x, which is equal to ln of 1 plus x all over x, where x is strictly greater than 0. And prove that g of x is strictly decreasing on 0, comma, infinity. Then we're going to interpret that result geometrically for this curve y equals ln of 1 plus x. Okay? So this will show what it says about the slope of the secant line from the origin, okay? And then finally, I may give a second proof. It depends. This is going to be long, okay? Or I'll assign a second proof for you guys to do, and you can comment in the chat um, what you think it is and how to do it, or you can contact me afterwards. But that that will be your homework, okay? All right, so let's get right to it, okay? So here's our problem, right? So you want to be able to show that this is strictly decreasing on the interval 0, comma infinity. And we want to interpret this geometrically from the statement, right? Right. So how are we going to go about this? So the way to go about it is we're going to be looking first at drawing some sort of graph here of what's happening. Okay. So you'll notice that we have the following. Okay. I'm going to draw the graph of y equals ln of 1 plus x. Okay. And the reason for that is because down here, we said about the slope of the secant line from the origin, right, to the curve y equals ln of 1 plus x, right? Right? So y equals ln of 1 plus x, right? We're going to draw that curve first, okay? So you can see this is y equals ln of 1 plus x, okay? And then we're going to also draw the secant line through 0, 0, okay? So we're going to the secant line, right, from 0, 0, right? So you can see that here. And since it's an ln function, there has to be an asymptote that is hitting at -1, but not approaching. Well, it is approaching -1, sorry. It is approaching -1, but the curve goes upwards and then goes to the right. Okay. So now we have, this is our function y equals ln of 1 plus x, and the secant line which goes through 0, 0. So since it's a line, we have to go through 0, 0, but it's going to intersect the curve at 2 points because it's a secant line. Okay. So this is an interesting concept. We've been able to draw it geometrically and see how it behaves. Right? So now we have this function right here. Right? So now we have the function right here. Okay. And we're going to go through step 1. Okay. So step 1 of the problem, right, on how to solve this. Okay. So we're going to do the following. Okay. We're going to say that if y equals ln of 1 plus x, x has to be strictly greater than 0. Okay. I'm not going to explain why. You should automatically know that x has to be strictly greater than 0 because it's an ln function and that's been shifted 1 unit to the left. Okay. Next, we will take a point on this curve, some coordinate x comma y. We're taking a coordinate x comma y, given the fact that we're going from the origin to the secant line. So we're going to have 2 points. Right, so we're going to have x comma ln of 1 plus x, right? Because x is x, y is equal to ln of 1 plus x. Okay. Now we're going to connect that point to the origin 0, 0. Right? Now we're going to connect that point to the origin 0, 0. So we have 0, 0, and we have x comma ln of 1 plus x. Okay. So how do we take the equation of a secant, right? It's just taking the slope, y2 minus y1 over x2 minus x1, right? I have 2 coordinates, x comma ln of 1 plus x, and we have 0, 0. We have 2 coordinates, right? One of x1 comma y1, one of x2 comma y2. So then you do y2 minus y1 over x2 minus x1. Okay, so that's the slope of the secant line. Okay, so this is my slope in reality. I should be writing this as a slope. Okay, so this is my slope. Right, so it's ln of 1 plus x minus 0. Right, that's my y2. So y2 and y1. ln of 1 plus x minus 0 all over x2. That's x1. X2 is x, right? And x1 is 0, right? And this simplifies to this on the right. So my g of x is equal to ln of 1 plus x over x. Okay, so we have that. Now, what we're going to look at, that was step 1. Okay. Step 2 now is to evaluate the function g of x where it's equal to ln of 1 plus x over x. Remember, there should be things going off in your head, right? You should be able to go back to the problem and look for some key words that will tell you on how to solve the problem. One key word here is that it says it needs to be maximized. G of x has to be maximized. So if g of x has to be maximized, okay, right, that means we have to take its first derivative, find critical points, right? So take g prime of x, and that's just the quotient rule, and gives us this, okay? So therefore, we get g prime of x is equal to all this, okay? Right? Just cleaning up and simplifying. All right, so that's what we get. And since x has to be strictly greater than 0, right? So x has to be strictly greater than 0. That's what the problem told us. Then we also know that that x squared has to be strictly greater than 0 because it's in the denominator of our quotient. Okay, so that's what we have. So the sign of g prime of x can now be found by taking x divided by 1 plus x minus ln of 1 plus x. Okay. So in reality, the whole problem now becomes x all over 1 plus x minus ln in parentheses 1 plus x, which is strictly less than 0. Right? Think about it, because now we're looking for we want to look for not only where g prime can be found, but how our function is behaving, right? So we have this expression now strictly less than 0 for all x being greater than 0. Okay. Now, equivalently, we can look at ln of 1 plus x minus x all over 1 plus x, which is strictly greater than 0. All you're doing is you're multiplying both sides by -1. You switch the inequality sign on both sides, and then the expression now becomes the reverse once you FOILed out the negative. Okay. Okay, so we've done that. We're on to step 3 now. right? So this is what we have. So take some time to absorb that. So step 3 now is to look at h of x, which is equal to ln of 1 plus x minus x all over 1 plus x. And since g prime of x, if we were to evaluate g prime, we also, when we simplify, right, that g prime of x, right, is minus h of x over x squared. Why did I put minus h of x over x squared? Remember, g prime of x is this. This is g prime, this whole expression. But look at the top. The top part is my h of x, right? In the numerator is h of x, which is equal to that jazz. I don't want to say the whole thing. You'll get bored. Okay, so that's h of x. I substitute h of x in to make it more simple. So minus h of x over x squared. Okay, so simple. Okay? Now, before moving to step 4, we need to, this gets a bit tricky. We need to prove, right? The problem is tricky, but it's not that tricky. Okay. So what we need to do is we need to prove that h of x is going to be strictly greater than 0 for all x greater than 0, right? So if you know anything about, this comes back down to elementary calculus, which you should know and be fluent in when it comes to maximums and minimums, okay? And increasing and decreasing functions. First derivative test. You should know that we need to prove h of x is strictly greater than 0 for all x greater than 0. And then g prime of x, which is less than 0, for all x greater than 0. Right? So this would prove that g is strictly decreasing. Okay? G has to be strictly decreasing. Okay? That's what it means. If you remember the definition of increasing and decreasing functions, it follows this formula, right? What I have above here. And since you want to prove that g is decreasing, we have to follow this. So the first thing is for step 4, we need to prove that h of x is strictly, h of x is getting greater than 0. Right? That's what we need to prove. We need to prove that. So we are going to prove that by taking h of x, which is equal to ln of 1 plus x minus x all over 1 plus x. Okay, so that's our h of x. Now the h prime of x, right? To get h prime of x, all you need to do is take the derivative, right? Now we're proving that h of x has to be greater than 0. So I need to take my first derivative. Okay, I have to take my first derivative, okay, of h of x and see the behavior, what happens. So h prime of x is going to be equal to all this. Okay, that's h prime of x. Then we collect like terms, simplify. You can see here we get this. Okay. So this is h prime of x. Now for x being strictly greater than 0, right? We're going to have x all over 1 plus x all squared, which is strictly greater than 0. Okay, where h prime of x has to be strictly greater than 0 for all x greater than 0. Okay? So think about that. Why do we need to find h prime? Because remember, we're trying to prove that h of x is greater than 0. If h of x is greater than 0, okay, then I also have to show that its derivative, I have to find its derivative and figure out it's greater or less than behavior, if that makes sense, in order to eventually get to it being strictly decreasing. Okay? page 5 then. And then from here, what we want to do is we want to take, okay, the next thing we want to do is take the left endpoint. Okay. So the left endpoint we know is that h of 0 is equal to, right? We're taking h of 0, our h of x function that we found earlier. Well, that was given to us. Right? That ln of 1 plus x minus x over 1 plus x. We substitute x equaling 0, right? Because that was the left endpoint of the graph, okay? Right, so at x equals 0, we get ln of 1 minus 0, 0. Okay, so that's what we have. And what we have here, what we're showing so far is that h is strictly increasing. Okay, h is increasing. A second. Yeah, h is increasing. I think you can agree with that, right? Because h of x is greater than 0 for all x greater than 0. And, right, your g prime of x, right? If you were to take g prime of x, you have g of x. If you were to take g prime of x, right, the g prime of x, we have to look at g prime of x because that was in our formula here, right? Right, we have to figure out g prime of x, right? G prime of x being less than 0 for all x being 0. So we need to evaluate that, okay? I mean, this is something that we can't avoid. We have to look at it, okay? So the g prime, okay, so the g prime of x, right, is equivalent to minus h of x over x squared, which is strictly less than 0, right? Because we want to evaluate when the behavior is less than 0, right? For all x being greater than 0, okay? So we need to evaluate that. And we're going to evaluate that by doing the following, right? We're going to look at g of x, right? Right. So remember, g prime of x was minus h of x over x squared, should be less than 0 for all x greater than 0. So we can automatically imply, if that's the case, right? Right, if it's less than 0, that g of x, our function, is strictly decreasing on the interval, right? On the open interval 0 comma infinity, right? So on 0 comma infinity, on 0 comma infinity, yeah, 0 comma infinity. Okay, that's 0 comma infinity, right? 0 comma infinity. So this is the interval that we have, okay? So far we've shown that it's strictly decreasing function on 0 comma infinity. Right, so this is what we've got, and this is a major milestone. We've been able to show that it's actually a strictly decreasing function. Okay, so given that information, right? So given that information, okay, so we have this. The next thing to do is to geometrically analyze this for step 5, right? Because, okay, sure, we've shown that g of x is strictly decreasing on 0 comma infinity, okay? But at the same time, we want to make sure that the function, right, is the slope of a secant line from the origin, which was from the origin to the point x comma ln of 1 plus x. Okay, so x comma ln of 1 plus x, right? So since g of x is strictly decreasing, we know that x is going to be small and the secant slope will be larger. That can be a little bit tricky to understand, but It isn't. If you look at the pattern here, it's very clear that when x is small, the secant slope has to be getting larger and larger. And when x is large, the secant slope has to be getting smaller. Okay. Right. So when x is small, the secant slope is larger. When x is large, the secant slope is smaller. Okay. So the secant slope from the origin is going to be maximized at the left edge. Okay. Think about it. It has to be maximized on the left edge. Okay. Okay. So now when x gets strictly greater than 0, there's no actual smallest positive x, which means that the maximum is not attained in the interior point. Okay. So the interior point, right? If you know some of your calculus 1, calculus 2, right? You have an open ball or a closed ball. Here's a ball, okay? And your interior point is inside here, right? The interior, right? And that's, I won't go into interior points, that involves a bit more analysis, okay? But this is the logic of how you would go about a problem like this, okay? Right. But this is just giving you a geometric analysis of the problem, right? If you got up to what we had here earlier, right? The strictly showing that it's strictly decreasing, you've pretty much solved the problem, okay? But this is a three-part problem, or a two-part problem, okay? Because you want to be able to prove some of the geometric anomalies here, okay? So instead, the largest possible secant slope is never bigger than 1, okay? Because as it approaches 1, as x approaches 0 from the right, we know that x approaches 0 from the right, we've shown that, okay? Then what you end up with, right? The implication is that the secant slope from the origin is strictly decreasing, okay? Strictly decreasing. We've shown that the secant slope is strictly decreasing, okay? And as x approaches 0 from the right, then its maximum, right? Its least upper bound, in other words, its least upper bound, or the supremum, is equal to 1, okay? Because the least upper bound is a supremum, right? So that's our supremum here, okay? And it is approached as x approaches 0 from the right, okay? But not when we have for every x being greater than 0. I hope that makes sense as to what is happening with the behavior of the function here, okay? Right? Because we have the secant slope. So what we've deduced here is that the secant slope from the origin is strictly decreasing and its supremum is 1, right? It's a very important distinction, actually, is because of the fact that most of us, when we say maximum, when when the actual correct statement is really the largest limiting value, or the least upper bound, or the supremum, okay? And on a serious exam, that would make the distinction, okay? It's very important to know that distinction. All right, so that is that's pretty much it from that point of view, of in terms of the proof, right? I will get you guys to yeah, try a second proof. There's another way to prove this, okay? There's another way to prove this. And that can be your challenge if you want, or homework that you want to do. You can always contact me in the chat, right? Just write things in the chat below if you don't understand something, you need help with something, or you have the proof, I'd be interested in seeing it. There's more than one way to prove things. Okay, so you can always point that out. Okay. But before I get going, there's something I want to mention. When it comes to an exam or final exam style test, um, what is very important is the result exactly, right? That you would want on the midterm or final to point out. Okay, so what's important here, right? So for final exam, okay, so for final, let's write down here for final. So for final exams, so for final exams, I want to point out the important information that we've deduced here. So let g of x equal ln of 1 plus x over x, where x has to be strictly greater than 0. Okay. And what you want to point out, which is important here, right? You want to get to the point here, right? All the important facts here, right? So then you're going to have this. Okay, you're going to have g is strictly. This is the important points that they want you to put on your exam. Strictly decreasing on 0 and infinity, right? Decreasing on 0 comma infinity. Okay, this is number one, first important point. Number two, that geometrically, okay, geometrically that g of x is the slope of the secant line is the slope of the secant line from the origin from the origin the origin 0 0 to the point and that point is x comma ln of 1 plus x. And then 3, that the secant slope decreases, right? So thus the secant that's the secant slope decreases 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 as the point moves right. Point moves right. Point moves right. 4, right? These are all important things for this problem. The largest possible secant slope largest possible secant slope is is approached as x approaches 0. Okay. So 0 from the right. Okay, and then finally, number 5 is that the limit as x approaches 0 from the right, in reality, because that's what we evaluated earlier, ln of 1 plus x over x is equal to 1. In reality, this limit is the same as taking the limit as x approaches 0 from the right of the suprema. Okay. All right. So I think that is it for today. Okay. If you want more hard calculus problems explained with full rigor and zero fluff and no nonsense, please like and subscribe. Okay. And if you are preparing for a midterm or final and need expert help with difficult calculus questions, check the links below. There'll be links below for coaching, expert coaching, or anything else. Comment this word. If you want more videos like this, there'll be plenty more videos like this. Comment secant in the chat below. There will be more videos coming hopefully this week. I might do one more this week. I'm busy. If not, there'll be next week. Next week, I'll either do more likely more problem solving videos. But I also do talking about how my brand is, some stuff about me, and how we can help you when it comes to using my systems technique for tackling hard problems. All right. Have a great day, guys. I hope you enjoyed the video. Like and subscribe again. See you next time.